Welcome to the channel, everyone. My name is Chad and I run the channel Chapman Cars and Tech. And in today's video, I'm going to show you how to design a simple full adder circuit and all the steps that are involved. In order to begin drawing our circuit, we need to discuss logic gates, and I want to start out with drawing the truth tables for the logic gates, which are Boolean operators. So we're going to start with the AND operator. So you want to AND two parameters or inputs. So A and B, A and B. So we start out by filling out these first two columns with 0, 0, 0, 1, 1, 0, 1, 1. It's basically we are counting up from 0 to 3. So AND is basically simple. It's basically like the English AND, where it is true when A is true and B is true. So 1 means true, 0 means false. So 0 and 0 is false, 0 and 1 is false, 1, 0 is false, then 1. Next we will start with the OR, which is kind of not exactly like a spoken OR. In this instance, OR is true if both are true or one or the other is true. So A, B, A, or B. So begin again with 0, 0, 0, 1, 1, 0, 1, 1. So A or B is false, so that's false. A or B, so A is false, B is true, so that's true. A is true, B is false, so that's true. And A is true and B is true, so A or B is true. And then finally we're going to be drawing out the table for an exclusive OR. So this is the OR that everyone is familiar with, the spoken English language OR. So A, B, A, exclusive OR, B. So 0, 0, 0, 1, 1, 0, 1, 1. So A and B, those are both false. So the result is false. A or B, so A is false, B is true, so you get a true result. A is true, B is false, so you get a true result. And A is true and B is true, so 0. So basically one or the other, but not both. The logical OR is one or the other, or both A and B is true. So now that we understand how logic gates kind of works, we're going to begin drawing our circuit. So just like we were doing before, we're going to draw a truth table, but since we're drawing a full adder, we're going to be dealing with a case where there is a carry-in bit. So A, B, C, I, N, so that's a carry-in. I want to bold that out a little bit. So this is our input side, and then this is our output side for our operation. So we're going to label these as such that it makes sense. So that'll make our design a little bit easier to work with. So on the right column, there'll be your sum, just like if you're adding actual numbers and then a carry out. So let's begin by counting from 0 to 7 in binary. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, and 1. So here we're just basically counting 0 to 7 because we have to take into account 8 different cases for our adder circuit. For a reminder, so we have 0, 1, 2, 3, 4, 5, 6, 7 in binary. So let's do our addition operations. So A and B is 0. There's no carry in, so that's 0 and 0. A plus B plus C. So we have 1, so we just simply add these numbers together. 0 plus 1 is 1. Same thing for this row right here. 0, 1. Here we're adding 2 ones together. That'll be 2, so 1 and 0. 1 plus 0 is 1. 1 plus 0 is 2, so 1, 0. 1 plus 0, that's 2, so 1, 0. 1 plus 1 is 3 in binary, so it'll be 1 and 1. To provide a little bit of context on why we designed a circuit like this, let's kind of draw a schematic for a 4-bit adder. So you have these adders here. And then you have your inputs. So usually this here at the top, right here, is will be a half adder. So there will be no carry-in bit. So what happens here with a half adder, you have A and B, and you have your sum, but you have a carry out. And the carry out will be the carry in for your full adder. So I'm just trying to catch up here. So basically you just repeat the sequence here, and then the carry out usually just gets thrown away unless you want to do something with it. And in this case, if you want to work with even more numbers, you need to have a bigger adder. It's been a while since I've been thinking about this stuff, so this is kind of like a really simplified explanation about how things work with this type of design. So now we're going to draw the Karnaugh maps for the adder circuit. So basically a Karnaugh map or a KMap is a tool that hardware designers use to map what's all in this area here to the left, the truth table, into a form where we can drive our our equations for our circuit. So you need a Karnaugh map for each of your outputs. So we'll begin with carry out. So C, carry out. So we start with a box. Since we are dealing with 8 cases, we need a box to work with our 8 cases. And we have to draw our inputs. So we draw an A here. So what's in this area here, under A, that's when A is true. Outside this area is A is false. And the same thing with B. And then also the carry in. So 0 plus 0 plus 0 is 0. So not A, not B, not C. 0. Not A, not B, and C. That is 0. Let's see here. Not A, B, but not C is 0. 3. Not A, B, and then C, so that's 1. 4. So now we're working with cases where A is true, so A, not B, not C is 0. And then 5 is A, not B, but C. So you put in a 1. 6, A, B, and not C. So that's true. So you put in a 1 here. And then for A is 1, B is 1, and C is 1, that is 1. So now we have a complete truth table for the carryout circuit. So now we have to do the same thing for sum. So sum So repeat for the sum column. So 0 plus 0 plus 0 is 0. Not A, not B, but C. So that's a 1 right here. Right here, so 1. Not A, B, and then not C is 1. So we're now going down for 4 or 3. So not A, but C is true and B is true. So put a 0 there. 4 is where we have an A is true. So A, not B, and C is 0 is 0. So that's a 1. 5, so A is true, B is false, and C is true. So go look at the far right, 0. 6, A is true, B is true, C is false. So 0. And then for the last box, look at the last column right here, 1. And now we begin writing our equations. And this takes a lot of practice, and I'm probably not going to be able to do a good job explaining it the first time on here. So basically you draw circles where you have ones grouped together. So you have a group right here. So that's lined up with the carry in and the B. So you have B plus a B and C. And then you OR it with the next group. So you have like the A zone and the B zone, and the circle lines up. So A, B, C, and then OR it again with this group. So A and carry in. Now for the KMap for sum, there is a little trick here. So if you see this checkered pattern here, basically all you got to do is exclusive OR all these inputs. So you have A, exclusive OR, B, exclusive OR, and C. So what I forgot to explain before for your logical gates, you have drawing representations. So for an AND, it looks like this. OR looks like this. This is an OR gate. So, and then and OR and exclusive OR equal, it looks like that. So now we have all the information we need to draw our full adder circuit. Let's begin to do that. All right, so now we're ready to draw a circuit. So we begin by labeling our inputs. So you have A, B, and then carry in. Carry in. So let's begin with the carry out circuit. So we start drawing lines that represent wires. So A and B. A and carry in. We just kind of just draw like a dot here to make a branch and make this little hop here. So that's A, B. And then B and carry in. So did a little sloppy job there, but that's okay. So we have carry in. So these are all separated by ORs. It's kind of like addition. So this is kind of like Boolean addition, and this is kind of like Boolean multiplication. So we're trying to OR three things together. So we have a thing called a 3-put input OR gate. So that will be our sum or our carryout. And then we need to draw the sections for the sum. So what's the best way to do this here? So we'll just kind of do that. And then we need one for B. And then we exclusive OR all of these together. And if you're not confused already, probably would have already be confused. This is how you draw a full adder circuit. If you like these videos or want to see if I get better at explaining this stuff just for fun, please do like, share, and subscribe. And we'll see you next time.